Okay, we have now this problem to solve this heat equation, and we are given the boundary conditions. These are the boundary condition, and this is the initial condition. So we are going to solve this problem by using separation of variables. Uh, so the solution, for this solution, let's say solution, we have to use the separation. We have u equal to x, function of x, and t, function, just a function of time. And then I'm gonna say I have x times t. Okay, now to sub in the equation, we have to find the partial derivatives term to x, which is going to be x prime t, and then the second derivative, which is going to be t, just like that. Okay, then we have also for time. For time we have time prime. Now I have to sub to the original equation. So I'm gonna have k times x time equal to okay, then I divide both sides by xt. Then I end up with I have xt and I have xt. I cancel t with t, x with x, then I have k times x over x, which equal to t first derivative over t. Okay, now I have to separate. Okay, now to separate, I'm gonna just say as previously, I'm gonna say, okay, all of these equal to lambda. But usually what they do, it doesn't matter, but I want to deal just with this part without a constant. So before separating, 1 over k over t. Now I'm gonna say equal to lambda. Now I can separate by saying equal to lambda, and then 1 over k first derivative over t equal to lambda also. This is gonna lead me to minus equal to 0, and then this also is going to lead me to this here is a first order ODE. Since it is a first order, it doesn't matter what lambda is, the solution won't change. So I just can solve this equation right here, which is going to be 1 over k dt over t lambda delta t. Then if I integrate both sides, I have 1 over k ln temp of time, in this case t is time. Here I have lambda t plus c1. Then if I multiply, I have ln time equal to k plus lambda plus t plus lambda times c1 is going to be just another constant. I'm going to just say c1. Then I have time t equal to e k lambda t plus c1. E c1 times e k lambda and t. All of these just another big constant. I'm going to just say t equal to c1 lambda k and time and t. Like that. Okay, that is your temperature. No, time. Oh, sorry. Yeah, that is time. Okay, now I need to deal with this part here for x. Now for x, this equation here for x, since it is a second order, the solution will depend on lambda. If you go to my previous video, I actually solved this equation. So you can watch that video to learn. But I'm gonna actually just recap. Okay, first I'm gonna go for case 1. For second order, you have to consider 3 cases. The first case, I'm gonna consider if lambda is 0. If lambda is 0, I have second order is minus 0 equal to 0. Then I have x 0. Now I integrate once. The integral of 0 is one constant. I'm going to say C2 because I have C1 already. And now I integrate again. C2, the integral of the constant is going to be C2x plus another constant, C3. Okay, now I need to find this constant, C2 and C3. Then I go back to the boundary conditions. The first boundary condition, u 0t equal to 0. I have that u xt equal to x t t. That means I have u when x equal to 0, 0t equal x 0 times just some function which is equal to 0. From here I can isolate x 0 equal to 0. Then when u l t equal to 0, if I do the same procedure, I end up with x l equal to 0. Now I'm gonna use these two conditions to find a constant. Okay, x0 is gonna be c2 times 0 plus c3 has to be equal to 0. From here I have c3 equal to 0. Then xl equal to c2 times l plus c3 has to be equal to 0. But C3 is already 0. We found it, so we know that C2 times L equal to 0. Then C2 is just 0. Then that implies that x, the function x, is 0, which leads to u xt being equal to x times t, right? So it's going to be just 0. So this is a solution for case 1. Now I go for case 2. If lambda is positive. If lambda is positive, I'm going to say, okay, lambda equal to plus alpha squared, because alpha is going to be any number. Alpha squared is always going to be a positive number. So from there, I have that, okay, alpha squared x equal to 0. Then from characteristic equation, 0, then you have r equal to plus or minus alpha, right there. Now, this equation, the solution would be x equal to c4 plus c5, like that, right? Or also c4 hyperbolic sine of alpha x plus c5 hyperbolic cos of alpha x. So that's your solution. But usually you use this when it is unlimited. For example, here for the solution, it is bounded is for a rod that you have here 0 and here x equal to L. So you have the temperature here and you have the temperature also here. So it is bounded from 0 to L. It is a limited rod, so I'm gonna use this solution. That means x equal to C4 x plus C5, like that. Okay, again, I have the boundary, I have the conditions equal to 0. I'm gonna to solve for the constant. I have x0, fx0 is gonna be c4, hyperbolic is gonna be 0 plus c5 cos hyperbolic, which is gonna be c4. Hyperbolic sine of 0 is just 0, and hyperbolic of cos hyperbolic of 0 is just 1, so c5 has to be 0. c5 is just 0. Then I'm gonna, for L, I have c4 L plus c5 is 0. Has to be equal to 0 according to the condition. This is just a constant. So we have c4 0. This also leads to xx c4 and c5 are both 0. So x equal to 0. This implies that u equal to 0. Usually for this type of equations, for the next problems, I will just solve for case 1 when lambda equal to 0, and I will go for the case where we get sine or cos, because the case where you get sine or cos are actually those that lead to the solution. When you see the hyperbolic and when you see the cos and sine hyperbolic, you have just to ignore that case because usually they don't lead to a solution. Okay, case 3. Okay, lambda, I'm gonna assume now it's negative. I'm gonna say, okay, minus alpha squared. Then I have the equation plus alpha squared x equal to 0. If I solve this equation, the characteristic equation equal to 0, then I have r equal to plus or minus alpha I. Then this leads to the solution C6, because I use C4, C5 already. I say C6 cos of alpha x plus C7 sine of alpha x. Now I'm gonna find again the constant 0. I have C6 cos 0 plus C7 sine 0. This is gonna be 1, so I have C6. This is gonna be 0 plus 0, and the condition for x0 has to be 0. That means C6 is 0. Then I have for xl, I have C6 is 0, so I cancel this part. I just have C7 sine of alpha L has to be equal to 0 because xl also has to be equal to 0. So from here, I see that, okay, if I say C7 equal to 0, if I say C7 equal to 0, then that implies that, well, there's no solution. Everything is 0. So usually here, what you do, I say C7 different than 0. That means I'm going to put sine alpha L equal to 0 instead. Then I have alpha L equal to n pi for n equal to 0, 1, 2, and 3, and so on, like that. Now notice that if you say n, okay, notice that if you say n equal to 0, then everything is just 0, right? N equal to 0 lead to the solution 0, so I'm gonna say n start to 1, 2, and 3. Because if n equal to 0, alpha just leads to 0. There's no really a good solution there. So I'm gonna say n start to 1, 2, 3, and so on. Yeah. So from here, alpha equal to n pi over L. That's your alpha. Then I take this. I have x equal to C6 is 0 equal to C7 sine of alpha n pi over L times x. for n equal to 1, n equal to 2, equal to 3, and so on. Because if you see, if you put n equal to 0, it just x just gives you 0. So it's just a 0. So we don't need that solution now. We need n equal to 1, 2, and 3. Then that means I'm going for u xt x times t. Then I have c7 n pi x over L times time, right, that I solved in the beginning. This one, this solution, which is C1 e to k lambda and t. Okay, okay, this is the equation that we got. Now I need to get rid of this lambda here. I have u xt is going to be c1 plus c7. I'm gonna just put a constant c e k and alpha, we got solution is minus alpha, lambda equal to minus alpha squared, right? So we have minus alpha squared t sine of n pi x over L for n equal to 1, 2, and 3, and so on. So you have that u equal to c e minus k, and alpha is n pi over L, so it's gonna be squared t sine of n pi x over L for n equal to 1, 2, and 3, and so on. Okay, now that we got this, since for n equal to 1, we're going to have one solution. For n equal to 2, is going to have another solution, right? So I'm going to say un, which depends on n, is going to be some constant that I'm going to say cn, that depends on n, e minus k, n squared pi squared over L squared t times sine of n pi x over L. 1, 2, 3, and so on. So after here, I have like a set of solutions. But according to the superposition, the principle of superposition, that states that if you have a solution, like, okay, if a function f1 is solution, f2 is a solution, f3 is a solution, so on, that means that if you multiply f1 plus f2 plus f3 is also a solution. And I can create a linear combination, that means c1 f1 plus c2 f2 plus c3, and so on, like that. So that implies that here I can just write the general solution as the summation of all the solution. I get rid of n here because now it's the general solution. Summation n start from 1 until infinity, cn e minus k n squared pi squared over L squared t sine of n pi x over L. So that is the general solution. Let me just write here like u xt equal to summation n equal to 1 infinity cn e minus k n squared pi squared t over L squared sine of n pi x over L, like that. Okay, now I need to know what is this constant here, right? I need to find the constant. So to find a constant, I need to use the initial condition. Initial condition, let me just go back. It was given here, was this function. So the initial condition was given x0, some function fx, which was 1 for 0x, L over 2 and was 0 for L over 2x and L. Let me just confirm it. Okay, yeah, that's the initial condition. Okay, I'm gonna find Cn. I have to sub ux when time equal to 0 to this equation that I found. It's gonna be summation n1 to infinity. I have Cn. When I put 0 here, for time 0, it gives me e to the power of 0 sine of n pi x over L, which is just the summation of n unto infinity. I have Cn sine of n pi over x, n pi x over L. So that is my initial condition. It has to be equal to this function here, fx, that I was given. Now, to solve, so I end up with this. If you see well, this is actually the same form as fx summation n1 infinity Cn sine of n pi x over L, which is just sine Fourier series. It's just a sine Fourier series where Cn equal to 1 over 2 times the period, in this case period minus, in this case the period 0 until L, or the period in this case if you were to solve it, fx sine n pi x over L dx. In this case, for our case, we have a row that is bounded from 0 until L. So P equal to L. So you have the constant C. Actually, the formula is actually 2 over L. Yeah, it's 2 over L. Just to make sure. Okay, now I have Cn equal to 2 over L integral from 0 to L over 2, because the function, the initial condition function, the initial condition function is given into branches. So I have to break the integral from 0 until L over 2 plus 2 over L integral from L over 2 until L. But the function here from L over 2 until L is 0. So this cancel this integral here. So I just end up with 2 over L, 0, L over 2. Then I have the function is 1 times sine n pi x over L dx. Okay, now from here, I have Cn equal to 2 over L integral 0, 0 to L over 2. I have sine n pi x over L dx. Now, what I have to do, I have just to solve this integral. I have to remember that integral sine ax dx equal to minus 1 over a cos ax. Then applying this, I have Cn 2 over L. Then I have minus 1 over a. A is going to be n pi over L times cos a is n pi over L x. This I'm evaluating 0 until L over 2. Then I have Cn equal to this cancel, so I have 2 n pi cos, when I sub L, I have n pi over L times L over 2. Minus, when I sub 0, I get 0. I get 1 because everything just becomes cos 0, right? So I get 1. So I have minus 2 n pi times cos of n pi over 2 minus 1. So Cn equal to 2 over n pi. Let's multiply by this minus 1 here. I have 1 minus cos of n pi over 2. That is my Cn. Yeah, this value is actually really to, because it changes, because if you actually see here, there is no specific number because it keeps changing. If n equal to 0, if n equal to 0, you get 1. If n equal to 1, you get 0. So it keeps changing, so just leave it like that. Then take the Cn, then sub here in the original equation. The equation we had was xt equal to the summation n equal to 1 and to infinity Cn e minus k n squared pi squared over L squared t times sine of n pi x over L. So I just have to sub the Cn we got, then ux t summation n equal to 1 and to infinity 2 over n pi times 1 minus cos n pi over 2 times e minus k pi squared over L squared times t, then times sine n pi x over L. So this is your solution to the equation that we had. So you can just use MATLAB to plot to see how the temperature changes with time by just building a code to do that. Yeah, because it's a very complex just to analyze like that. So you actually have to use coding to get the values for temperature. And we just apply directly summation of variables. No, summation, sorry. We just apply directly separation of variable because as you can see, the boundary conditions are both are 0. Here and here 0. If they are not 0, you actually have to use, you cannot apply separation variable first. You have to do something that we're gonna see later in the next videos.